Below are 8 crates of differing mass. Each crate is being pulled to the right at the same constant speed. In part A, we are to rank the magnitude of the force exerted by each rope on the crate immediately to its left if the frictional coefficient between each crate and the surface is the same non-zero value. Okay, so I don't know what that coefficient is, but it's the same for all. And because the crates are moving, that would be a coefficient of kinetic friction, so let's just call it mu k. Now, each crate is being pulled to the right at the same constant speed. If the speed is constant, the acceleration in the x direction is equal to 0, and also the crates are not accelerating in the y direction. And I can use Newton's second law, which says the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, so that gives me the sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, and in this case, the sum of the forces in the y direction is equal to 0, since the acceleration in the y direction is equal to 0. Okay, now I am going to draw a free body diagram, and I'm going to start with the 3 blocks on the top, and I'm going to treat them as one object and do the free body diagram for the system of the 3 blocks. So that means the force that rope C exerts on the 1 kilogram block and the force that rope C exerts on the 2 kilogram block, since they're equal and opposite, they will cancel out. Same thing for rope B, so I just have the force that rope A exerts on the train of 3 blocks, and then I also have friction, so I have, that would be kinetic friction acting in the opposite direction. And the sum of the forces in the x direction is equal to 0, therefore the force in rope the force in rope A must be equal to the force of kinetic friction. Going back to page 57, in Model 2, we have the force of friction is equal to the coefficient of kinetic friction times, this is the normal force. Which means I also have to look at the forces that are acting in the vertical direction. For whatever blocks you look at, whether it's the train of 3 blocks or an individual block, you're going to have the force of gravity acting downward and the normal force acting upward. So we have, since the sum of the forces in the y direction is equal to 0, the normal force is equal to the force of gravity, which is equal to m times g. So it's whatever mass you have in your free body diagram times g. And for the force of kinetic friction, we have the coefficient of kinetic friction times the normal force. That means for us, since the normal force in this case is equal to the mass times g, the force of kinetic friction is coefficient of kinetic friction times the mass for whatever you did your free body diagram for times g. So this would be mu k times m times g. So to finish this, we have to figure out what mass we did our free body diagram for. Well, this was the top row where we have 1 kilogram plus 2 kilogram plus 3 kilograms. So that would be mu k times 6 kilograms. I'm going to leave the units off, times g. So that's what we have for A. For B, I'm going to do just the 1 kilogram block and the 2 kilogram block. So if this is my system, we have rope B exerting a force on that system, and we still have the force of kinetic friction. This is not the same as the force of kinetic friction that we had here. By Newton's second law, we have force B is equal to the force of kinetic friction. Since the sum of the forces in the x direction is equal to 0, the force of kinetic friction is mu k times the mass times g, but in this case the mass is 1 plus 2. So I know that force A is greater than force B. Then if I look at the last block, so this is just C, I have the force that rope C exerts on the 1 kilogram block and the force of kinetic friction. Force C is equal to this force of kinetic friction, which is mu k times this mass, which is 1, times g. So force C is smaller than force B. So if I do the ranking just for those, A is greater than B is greater than C. So as you go down the chain this way, the force is decreasing. I can do the same thing for the next train of blocks. So I have force D, I have a force of kinetic friction here. Force D is equal to the force of kinetic friction, which is mu k, times the mass of 1 plus 2 plus 3, that's equal to 6, times G. So D and A are equal to each other. Let's say D is equal to A. Then if I move down the chain and just do the 3 kilogram block and the 2 kilogram block, I have rope E, which is touching those two blocks, and I have the force of kinetic friction. This is just the free body diagram for the forces in the horizontal direction, and I have force E is equal to the force of kinetic friction. The total mass is 5, so that's 5 times G. So E, since force B was 3 times mu k times G, E is somewhere in between A and B. Let's say A is greater than E is greater than B. And then if I just do the 3 kilogram block, I have a force of kinetic friction going this way. This is the force that rope F exerts on the 3 kilogram block. The force in rope F is equal to the force of kinetic friction. That's equal to mu k times the mass of 3 times G, which is the same as B. So B is equal to F. And then let's do the last free body diagrams up here. So I have the force that rope G exerts on the 3 kilogram block, and I have a force of kinetic friction going this way. Kinetic friction is mu k times m times G, as long as the normal force is equal to the force of gravity, which it is for all the cases that we have here. So this is equal to mu k, the mass is 3, and then times G. Then this force is equal to the force of kinetic friction, which is mu k times 5 times G. This is 3, and B and F were also 3, so G is equal to B and F. This is 5, and I think we had another one which is equal to 5. E was equal to 5, so this is equal to F. So finally, A and D were equal to each other, so A is equal to D. That's greater than B and, no, that's greater than E and F. E and F. That's supposed to be an H. This was F. This one's H. This was force H. Okay, so E and H are equal to each other. And then B and F and G are all equal. So B is equal to F is equal to G. And then C. In part B, we want to rank the magnitude of the force exerted by each rope on the crate immediately to its left if the frictional coefficient between each crate and the surface is 0. If the frictional coefficient between each crate and the surface is 0, what happens to all of the forces that we had in part A? They all depended on something times the frictional coefficient. So if the frictional coefficient is 0, all those forces are equal to 0, therefore they are all equal to each other. So A is equal to B is equal to C is equal to D is equal to E is equal to F is equal to G is equal to H, and all are 0. If they're moving at a constant speed, do you have to apply a force to keep them moving at a constant speed if there is no friction? No, that is what Newton's first law tells us. If the net force is equal to 0, then the acceleration is equal to 0, and your blocks will continue to travel at the same constant speed.